So, welcome, and today we are going to talk about Asaro-Tiller-Greenfeld instabilities. They are also known as ATG instabilities in the literature. And here is what we are going to discuss. We will first find out what ATG instability is, and there are two ways of analyzing ATG instability. In fact, in ATG, Greenfeld used the variational analysis and Asaro and Tiller used the perturbative analysis. So, I am going to show you how Greenfeld did the variational analysis. That is the first part, where we want to look at the energy of a wavy interface and want to compare it with a flat interface. And as you can see, when there is no waviness, the energy that we write for the wavy interface becomes the same as flat. So, about flat we are now looking at wavy, and the first derivative becomes 0. Second derivative is negative, which means that the wavy interface has a minima with respect to the waviness, okay, when you compare with the flat interface, which means any interface should become wavy. That is basically the conclusion that we are going to draw. So, I am going to prove that. That is the first part. Second part is you can also do a perturbative analysis, which we have been looking at. I impose a wave of a given wavelength, look at its amplitude, what happens to it with time. For the same problem, you can do either, like I said, Asaro-Tiller-Greenfeld instability. Greenfeld used the variational arguments, Asaro and Tiller did the linear stability analysis. But just to give you some more information, I will do the perturbative analysis, but I will do it for a thin film assembly. Okay. And so, we will write the diffusion potential, we will look at the growth rate. Finally, there are some nice phase field results that Sushil had generated. So, I will show them, but the aim in this course is to get the same things using PFC, where you will see that you can transition from the elastic to the plastic regime fairly effortlessly, right. Whatever I am going to show today is only elastic regime. We assume that we are within the linear elastic regime. So, there is no possibility of, for example, some plasticity creeping in. Even though experiments you will see there are cracks that propagate, dislocations that form and so on. Those cannot be done with the analysis that I am going to discuss today, but you will see we do modeling basically because we want to relax many of these assumptions, approximations. With phase field you can relax many of them. But if you do phase field crystal, you can even go beyond the elastic regime and plastic deformation will also be accounted for, which you can do with the codes that you have. With a little bit more of effort, you should also be able to see. So, this lecture is based on this Hilliard's premise, which I like. So, I am going to show you all the details of the algebra. And this is what you have been seeing with Kuo-An also. He has also been showing all the details. Some of them might be trivial for some of you, but it is useful for others who have difficulty in following. So, we will try to, so you can see there are 75 slides. So, I am going to go as detailed as possible, and these slides then you should be able to follow most of this literature with the help of these in case you have any difficulty. So, let us start with ATG instability. And here are a couple of photographs that I asked our daughter to take a notebook and press. When you press, a thick notebook bulges on both sides. This will be what will be called as a symmetric breakup in the ATG literature. And if it is thin, then it buckles on one side, which will be called as anti-symmetric in the ATG literature. So, why does the notebook buckle? When you are trying to press, there is elastic energy that you are storing into the notebook, and the notebook can relax these elastic energies if it buckles, right. So, it is always favorable for a stressed system to relax by, why is it able to buckle? Because the surface next to it has a less compliance, right. It is less stiff, more compliance, less stiff, right. You have this notebook, compared to notebook you have air or vacuum next to it, which will allow this deformation, and so the system will do this, so that it can minimize the total elastic energy. So, this kind of wrinkling is very common It need not be like this. I do not know, some of you might have seen on your books there are sometimes a shrink wrapping of plastic sheet which then buckles, right. So, it is very common, stressed sheets always buckle because it is always energetically favorable. So, there are several examples, and one of the nice things about the ATG is that it can range from this kind of strain induced roughening of thin films or substances. Silicon germanium is an example, 1992 there is a nice paper, and there are lot more in the thin film literature, because this is one of the mechanisms of thin film growth called the Stransky-Krastanov, where islands form and then the islands meet and then make the film. And the island formation can be understood in terms of ATG, and so you can tune it with stress and you can get quantum dots and so on. So, this is a whole field. Stress induced morphological changes in solid helium in contact with liquid helium is a classic case where many of these theories are tested, because you can have lot more of control over things. And stress induced cracking of minerals is very important for people in earth sciences and geology and so on, because you go down the earth and you have these minerals and they are in contact with their own solution, because there is always water nearby, and this mineral is under stress because it is below the earth's crust, and so it is solid, non-hydrostatically stressed in contact with a liquid. And there are very nice experiments that are done in the lab. You take a potassium or sodium crystals, I think Cl, NaCl or KCl, and you press them and you keep their own solution next to them, and then they develop all these cracks. You release the stress and the cracks heal. So, this is due to ATG, and there are some very nice papers experimental on that, which are of relevance. And of course, Asaro and Tiller were looking at stress corrosion cracking, because as you can imagine, if you are solidifying a metallic system, and solidification stresses will lead to non-hydrostatic stresses in the solid, and that solid is in contact with its melt. So, its surface will tend to break up. Okay. So, that is the context in which Asaro and Tiller were studying. And the polymerization induced breakup of films is also very common. Again in 1992 there have been some papers. So, the film initially wrinkles and then the troughs become so sharp that there will be cracks that will run through. So, very uniform cracking of film, polymer film, and the stress is coming because of polymerization that puts a stress on this film and it breaks up. So, as you can see, minerals, they probably crack at the order of meter length scale, and you have roughening of thin films which are probably on the nanometer scale, and somewhere in between you will see micron scales and millimeter scales and so on. So, it is a phenomena that happens at different scales, but the physical reason is the same. It is basically elastic stress relaxation. Here is one schematic which shows why a film, for example, is expected to undergo ATG instability. I have a substrate and I have a film, they do not have the same lattice parameter when they are in equilibrium by themselves. If you form a film, it will have a lattice parameter which will be different from if you deposit it on a substrate, because the substrate being a larger system imposes its lattice parameter on the film, which is very thin, which means the film is under compressive or tensile stresses depending on what its lattice parameter is compared to the substrate. Now, if the surface, film surface is flat, it has to have the same lattice parameter throughout the film. So, there is a homogeneous strain that it has to store. Suppose if the film surface becomes a little bit sinusoidal, and if you assume that the film would like to have larger lattice parameter, for example, you can see that at the peaks it can relax to the larger lattice parameter, but at the cost of making the lattice parameter still smaller at the troughs, which means once this sets in, it is self propagating. The chemical potential at the troughs is higher, so the atoms will leave and attach where the chemical potential is lower, which is the peaks. So, this process will keep on happening, and hence you will have a undulation growing, and finally it will lead to breakup or plastic deformation and so on. This is static, where I have assumed that I have a given film and how it is evolving with time. But suppose this undulation sets in and your film is still under growth, the atoms or adatoms that are coming and attaching to the film will still find it easier to attach at the peak, where they can be much more relaxed than at the troughs, which means that these undulations once set in, as you are growing the film, will enhance the undulations. So, in the ATG literature, there are two kinds of ATGs that are talked about. The first case where, for example, you grow a film and then post film growth you try to anneal and then it breaks up into islands, that will be called as static ATG, as in no more material addition. But as you are growing the film, when it breaks up, that will be known as dynamic ATG, because as you are growing the film itself, ATG instability sets in and gets enhanced and leads to breakup of the film. Okay. So, we will primarily look at static ATG in this lecture, but I will point out to some literature on dynamic ATG, and if you have an idea about these methodologies, then it is fairly easy to do it. Yeah.
So, there is different in mechanism in static adatom on the trough to add on the surface than the dynamic ATG, or it is the same mechanism?
The driving force is the same, it is the chemical potential difference. But if you have static, then you have to transport material from one part of the film to another part. That can happen in many different ways. It can be bulk diffusion, it can be surface diffusion, it can even be evaporation, condensation, or dissolution, deposition. In the case of, for example, solid in contact with its own melt, or a solution, where in one part the salt will be dissolving in minerals, in another part it will be getting deposited, right. So, the mechanism of mass transport has to come into play if it is static, because you are trying to change the material is the same, the amount is the same, you are trying to move material from one point to another. So, the kinetics will depend on how you are transporting. On the other hand, when you have dynamic ATG, you are depositing material, right. It does not have to take material from one end and put it another. The material that is coming in can preferentially deposit at one place, right. So, there is a difference in terms of where the material is coming from and what is the mechanism of that material getting transported to that point, and there is no difference, because in all cases it is anyway the chemical potential or the elastic stress relaxation that is leading to it, right. Okay. So, ATG is a elastic stress driven instability, specifically it is a bulk elastic stress driven instability. In the case of thin films, for example, you might have steps might have their own elastic interaction and so on. We are not talking about that, we are talking about the bulk energy that is stored in the film. There are two ways to analyze. Of course, you can minimize the total energy and look at what happens, or you can put a small perturbation and see how it grows. Okay. So, minimization is ideal for studying static ATG instability, because you take a flat interface and then you compare it with a wavy interface and you show that the energy is getting minimized for the wavy interface, you are done. But even though this is a variational problem, and I will show you how it is done, we finally do not obtain the equilibrium shape. This is a more generic thing. When you are doing elasticity, in general you do not get equilibrium shapes, because elastic energy is shape dependent. So, you have to analyze all sorts of shapes before you can decide what is the equilibrium shape. So, in general you do not get the equilibrium shape, but one might think that, oh, this is variational and so finally I will reach the end state and so on. That is not the case. In the case of perturbation, because we are taking into account the kinetics, how the material is getting transported, so you will also get the kinetics of the instability. So, it is much more suited for dynamic problems, right. You might deposit adatoms and how they move and what is their kinetics and so on can be easily incorporated, whereas in the case of variational that is not easy, especially if the material is changing then that constraint, that overall volume is same, is not true. So, it can become more complicated. Having said that, it does not mean that you can't do variational for the other problem, or you can't do perturbation for the static problem. You can do both. It is more easier to do one or the other depending on the situation. So, we are going to do both. Let us start with the variational analysis. And for variational analysis, I have two references, both from Grinfeld, and this is a very nice report from the University of Minnesota, the stress driven instabilities in crystals, mathematical models and physical manifestations. And long back in 96, 97, when I was looking at some of these things, you have to write to them and they will post you a hard copy. Okay. So, I had gotten a hard copy from University of Minnesota, but I think nowadays you can get this online, you can download this report. Mostly the same material is published by Grinfeld in Journal of Nonlinear Science, the stress driven instability in elastic crystals, mathematical models and physical manifestations is what he called it. Even though both of them have all the details, some details are better given in one than in the other. Maybe there was a review process, maybe there is, or he improved on the report himself and so on. So, some mathematical details, it is easier to follow if you have the journal paper, okay, and some things are better explained in the report. But primarily, I mean 90-95% is the same in both, there are small differences. So, if you have some doubts, sometimes it is useful to have the other document also with you. So, I am going to follow basically these two papers and I am going to show you all the steps, that is all I am doing, right. I mean Grinfeld will write one and will write the result, and there are a few mathematical steps and it takes for a while for us to figure it out. Maybe for people who do it day in and day out, those are common, they are very obvious maybe, but not for us, at least not for me. So, I am going to show you all the steps that I filled in, how I got the details of this analysis. So, let us do it in detail. So, we take an unperturbed film vapor interface. So, the system that we are considering is that I have a film freestanding, and I say that only one surface is allowed to change, the rest of them were kept constrained. So, on the surfaces where I have prescribed displacement, I have called it as capital gamma. So, in the initial one where I have the unperturbed film surface, all surfaces are capital gamma, which means I know the displacement. What is the displacement? They cannot have any displacement, they have to be bounded by this. And then on one of the sides I allow for changes to happen on the surface, and that is called a free surface. This one is a free surface, and gamma is where displacement is prescribed. The prescribed displacement is 0, okay, and a free surface you can think of as prescribed traction, right. And what is the traction that I prescribe? That makes it a free surface. So, gamma is where traction is prescribed and it is traction free, and capital gamma is where displacement is prescribed and the prescribed displacement is 0. Okay. So, this is the case we are looking at. Now, let us say that I write the energy for this system and I call it as script energy F flat, and for this system I calculate the energy and I call it as wavy. Okay. This is the energy that is from the elastic contribution to the free energy of the system. Now, you can see that when this capital gamma goes to small gamma, there is also a change in interfacial energy, interfacial area, and hence a interfacial energy contribution to the free energy. When we do the variational analysis, first we assume as if that interfacial energy contribution is 0. Okay. At the end we will see what is the effect of including the interfacial energy. So, this analysis is done purely based on the elastic energy contribution to the free energy. The interfacial energy contribution we will discuss at the end after we have the result for the elastic energy part. Okay. Okay. So, what is our aim? Our aim is to show that EW minus EF is less than 0 is always true, meaning it does not matter what kind of waviness I am putting, it should always have wavy surface should have lower energy. That is what we want to prove, provided the waviness is very small. Okay. I am going to assume that the waviness is very small. What do we mean by the waviness is very small? You will see when I do the analysis, there are several assumptions and approximations that I make, which will tell you what I mean by small waviness. Okay. And so, F is flat, W is wavy, the script E is basically the elastic energy contribution to the free energy. How do we prove this? We can prove this by first thing, okay, what do I mean by the small disturbance? So, I assume that this gamma that you had, right, this can be described by a parameter called disturbance parameter epsilon. Okay. For those of you who have done variation, this is like the variation, and I will also demand, as you can see that there are portions of the interface, for example, at this point and at this point, there is no variation, right. All the allowed variations should still meet the prescribed displacement at that point. Okay. So, we are thinking of describing the variations in that surface structure using a disturbance parameter epsilon, and I assume that this epsilon is far smaller than 1. Why is this assumption made? So that if I Taylor expand the energy of the wavy surface with respect to the flat surface, when there is no waviness, when the disturbance parameter is 0, that is equal to flat. If I expand in the Taylor series expansion, I am going to neglect all terms of the order of epsilon cube and above. So, my epsilon should be small enough that this approximation is valid. That is what I mean by small waviness. Okay. So, I can describe, can parameterize the disturbance on the surface using a parameter epsilon, and the epsilon is small enough that epsilon cube, epsilon power 4, etc., if they appear, I can assume then that they are small enough that I can neglect them. Now, the aim is to prove that if I want to prove that this is minima, I need to prove that this is equal to, right. When there is no waviness, I should recover the flat energy, and I should prove that this is equal to 0, because this is arbitrary epsilon, and if this has to be a minima, right. What is the definition of minima? We always think that if there is a minima point, then on either side I go, it should increase. But if you have a term which is epsilon, if you go on one side it will increase, if you go on another side it will decrease. So, it cannot be there. So, this is the necessary condition for the minima, right. This is classical calculus. In high school probably you are taught why the first derivative should always be equal to 0 for the extrema. Minima or maxima does not matter. For maxima also same argument holds. If this is maxima, then on either side I should go, it should decrease. But if you have the first term, epsilon term, you go on one side it will increase, you go on another side it will decrease, because it changes sign, and those changes of sign are not acceptable for minima or maxima, because they have to be 0, they have to be either positive or negative. So, the only way to make sure is that there is no term that comes from epsilon itself. So, which means the coefficient that is multiplying in the front should become 0. So, that is the necessary condition. Now, if you take a system in which there is no first order dependence, second order, see this is square. So, this will always be positive whether you go to the left or right, which means the term that is multiplying it should be negative for it to be a minima and positive for it to be a maxima. So, this is the sufficiency condition. So, our aim is to show these three conditions or valid for the system that we are considering using the elastic energy basically, right. That is what we want to do. That is what is shown here. The energy of the wavy interface when the disturbance parameter is 0 should be flat surface, energy of the flat interface. First variation of elastic energy with respect to the disturbance parameter should be 0, that is the necessary condition for the energy to be extremized. Second variation of elastic energy with respect to the parameter, the disturbance parameter should be negative, because that is the sufficiency condition for the extremum to be a minimum. So, we want to do this. Now, as you can see, some things are easy and some things are hard, because if you have prescribed displacement etc., it is very easy. Prescribed traction is a bit of a pain. So, most of the effort is going to go into this gamma surface, rest of it is fairly trivial as you would see. So, let us do one by one. So, if you obey these three conditions, then you will get the energy of the wavy interface to be always less than the flat interface for small enough epsilons, and when I say small enough, it is small enough that epsilon cube and higher order terms can be neglected, that is what I mean. Okay. So, because we are trying to solve the elasticity problem, I need to find the displacement field from which I can derive strain, from which I can derive stress. So, that is basically the strategy always, right. You always write del squared u and you want to solve. Okay. So, let us say that ui is the equilibrium displacement field. Now, I am going to assume that the ui can be written as an expansion in terms of the disturbance parameter for a wavy boundary. So, ui, which depends on the position x and the disturbance parameter, is some ui 0 plus summation p 1 to infinity epsilon to the power p ui to the power p at xk. So, this is the expansion that I am going to write in terms of the disturbance parameter. Remember, I have assumed that epsilon is small enough that in all these expansions higher order terms can be neglected. Okay. So, which is what we are going to exploit, and this kind of series solutions and comparing coefficients is something that Kuo-An also has done, and we are going to use the same strategy here also. Now, this displacement field should obey the equation of mechanical equilibrium. What is the equation of mechanical equilibrium? This is the equation of mechanical equilibrium. Okay. Why is this the equation of mechanical equilibrium? We generally write del dot sigma equal to 0, and I am assuming that sigma obeys the Hooke's law. This is linear elasticity or hyperelastic material. So, I am assuming Hooke's law, and we also know that epsilon KL can be related to the displacement field by symmetrizing the gradient of the symmetric field, right, the displacement field. So, it is half ui uk comma j plus uj comma k, where my notation comma k means uj comma k is nothing but dou uj by dou xk, right. Now, C has symmetry properties that follows from the fact that the stress is symmetric tensor and strain is symmetric tensor and so on, and stress and strain are symmetric tensors for two different reasons. Okay. I will not go into those details, but you can look up some textbook like Nye or Mura, they show these symmetry properties. So, in writing this we have assumed all those symmetric properties. Okay. So, dou by dou xj C I j k l dou u k by dou x l equal to 0, we are using Einstein summation convention. So, k l etc. will get summed over, j will get summed over. So, this is a vector equation. Okay. If you are in 3D, there are 3 equations here, and C I j k l is the elastic moduli tensor, and the displacement gradient tensor is del u, and its a symmetric form is basically what the strain is. Okay, and the xi are the components of the position vector. So, this equation of mechanical equilibrium should be satisfied by the displacement field that I am assuming, right. Now, if I substitute this ui in the equation of mechanical equilibrium, because one side is 0, look at the first term, that is a constant anyway. So, you take gradient, it will be 0, right, and you take gradient of these, epsilon is a disturbance parameter. So, you will have epsilon to the power 1, 2, 3 etc., and there are no powers of epsilon on the other side. So, all of them should be 0, okay, which is what is shown here. If you substitute the expansion into the equation of mechanical equilibrium and compare the coefficients, you will find that within the body all these u, k, p, p is 1, 2, 3 etc. up to infinity, they all should be 0. Okay. Now, that is not the only condition. Remember, equation of mechanical equilibrium is a partial differential equation, and a partial differential equation is not specified unless you specify boundary conditions. And so, we have two types of boundary. On one boundary I have prescribed displacement, which is what this Aij is the imposed homogeneous strain, and I have traction 0. Remember,Cijkl dou uk by dou xl is basically sigma ij. This is sigma ij. Sigma ij dotted with nj basically is the traction, and traction should be 0 because that is a free surface, that is the boundary condition I am imposing, right. This is what I said, I am imposing a boundary condition. What is the boundary condition I am imposing? These are the boundary conditions I am imposing. So, you can take the u solution that you are having and you can substitute into this condition also, right, on 8, on 9 and on 10. It has to obey these two also. You cannot take a ui and call that as a solution to equation of mechanical equilibrium if it does not obey the prescribed displacements, for example. That is not a valid solution for me. My solution should obey the prescribed displacements also. If I have a solution and if I substitute in this traction boundary condition, if it does not satisfy, that is still not a solution for my problem. So, in addition to solving the equation of mechanical equilibrium, the displacement fields that I choose should be such that it obeys the prescribed traction and prescribed displacement boundary conditions. Now, prescribed traction is going to take some work, so I am not going to do that. Before that, I am going to take the prescribed displacement boundary condition, and I am going to take my ui and substitute here on the left hand side, right. You can do that. What do you get if you do that? If you substitute 7 in equation 10 and compare the coefficients, what do you get? Do you see why it is 0? What I have is ui is okay. Now, if I substitute for ui, this ui 0 plus summation p equal to 1 to infinity epsilon p ui p xk, right. You look at the terms, aij xj will give you ui 0, right, and all the epsilon powers will be 0 because on the other side there are no powers of epsilon. So, that is how we get this solution, that using this displacement boundary condition, if you substitute, you will find that uip are uniformly 0. Okay. So, within the body we know what the condition uip should obey, and where the displacement boundary condition is prescribed, we know that our uips are all 0, okay, which is understandable because there is a disturbance parameter and I am already prescribing displacements there. There can be no disturbance, which means any contribution that comes from that part of the displacement will be 0. This is not surprising, I mean I am just showing it mathematically. Now, we want to substitute this solution, series solution ui 0 plus summation epsilon to the power p uip into the traction boundary condition. But traction boundary condition is a little bit more work because the location of the boundary, right, ui at xk, but the boundary itself is moving, which means at x, depending on the disturbance parameter, it has different x's. That is where the boundary is. So, the boundary is not fixed, that is why it requires more work. So, how do we deal with this? We deal with this by saying that the boundary gamma is defined with a parameter, so gamma of epsilon, the same disturbance parameter, but this disturbance parameter multiplies a delta of x, and the delta is like your variation. It is prescribed at the end points x equal to 0 and x equal to L. At other points it has value depending on what the epsilon is. Okay. Now, because this is where the static ATG is coming in, right. If I have a film like this, if I want to make this surface undulating, I cannot make this surface undulating by taking it like this, which means I need more material. Where is it going to come from? Right? In dynamic it can come, because I might be throwing some flux and I can add how much flux is there, with time it will add up. But I am doing static ATG, which means this cannot happen. The disturbance, whatever delta that I am putting, if you integrate, that means it will be like a sine, cos, whatever combinations of them. So, if some place it increases, in some other place it had better go down, right. So, that is what this condition is. If I integrate 0 to L delta of x dx, it should be 0. This is basically mass conservation. Okay. This is what makes our analysis for static ATG. Okay. So, I have this constraint that delta of x dx should be 0. I also have this constraint that at the end points x equal to 0 and L, it should have prescribed displacements. It cannot have any variation. The disturbance parameter, irrespective of what it is, it will not lead to any changes in the position. In between it can change, and it changes in such a way that the total mass is conserved, and that is what is described by this. So, I have parameterized the free boundary gamma in terms of the disturbance parameter, mathematically speaking, right. Now starts the algebra. Let Ni epsilon be the unit normal at x for the boundary gamma epsilon. So, what do we mean? I have this, these are all capital gamma, right. Now, I have this interface, this is the x direction, and you can see that at different x the normal is different, right. So, I want to know what is the unit normal for given epsilon on this boundary at a given x, right, at different points. The components of the unit normal are, you take 1 plus epsilon times d delta x by dx whole squared, you take square root of this, that is d, n1 component is minus 1 by d epsilon d delta x by dx, n2 component is d inverse. Have you seen this? Do you know why this is so? No? So, this is there in many different textbooks. Okay. So, let me first give, so if you look at the discussion on space curves in Riley, Hobson and Benz, section 10.3, it is there. Okay. You can also take this classic calculus textbook, Thomas Finney and Ware, Calculus and Analytical Geometry, and it is the discussion on principal unit normal vector in chapter 11, where you will see this formula. What does the formula say? If a curve is parameterized by s of x, in our case it is getting parameterized by epsilon delta x, then the components of the normal will be given by, this is basically 1 plus dou x by dou x whole squared square root, which is what we are doing, 1 plus epsilon d delta x by dx whole squared. Square root of that is basically, that is what k is. So, the n2 is 1 by k, n1 is minus 1 by k dou s by dou x. Okay. Now, this is also there in some form in the thin film textbook by Freund and Suresh. I do not know how many of you have seen. I have a reference, same result. I have another reference from Freund and Suresh later. Just to tell you that this is very common. This is related to the geometry of such parameterized surfaces, how to get normal. If you have a surface that you can describe, how to get its normals at any given x, this is the formula. Okay. So, that is the result that we are using when writing. I mean, this is the place, if you read Grinfeld, he will say obviously the normal is this and so it is this, right. So, you need to know why that is the normal, you can go. I like Riley, Hobson, Benz, but the other book is also a classic, Thomas and Finney. I do not know how many of you use Thomas Finney any time for calculus. Okay. So, those are the normal components. So, if you take dou by dou epsilon of n1 and evaluate it at epsilon equal to 0, that is nothing but minus d delta by dx. Why? If you take dou by dou epsilon, you will still have minus d inverse, but look at d inverse. What was d inverse? 1 plus epsilon d delta x by dx whole squared. That is why I am evaluating at epsilon equal to 0, right. Otherwise, the other thing minus d delta x by dx will automatically come by differentiation of epsilon itself, but d inverse depends on epsilon. So, if you evaluate at epsilon equal to 0, then dou by dou epsilon n1 is minus d delta x by dx. By dou epsilon of n2 is 0, because n2 is just d inverse, right. And so, you have 1 and you are putting epsilon 0. So, you will get 0 from there. So, you can write this. So, this is just notational. Dou by dou epsilon of ni, you can write it as minus d delta x by dx delta I 1. So, when I is equal to 1, it will be 1, when I is any other value, it will be 0. Delta is the Kronecker delta. So, this is just a shorthand notation. Why do we need dou by dou epsilon of ni at epsilon equal to 0? You will see, and that is why I am deriving this result to keep this. So, this is basically the evaluation of the normals n1 and n2. Okay. Now, we can take the solution and substitute in equation 9. What was equation 9? Let us remind ourselves, and what is equation 7? Let us remind ourselves.Cijkl dou uk by dou xl nj is equal to 0. That is the traction boundary condition. That is what we want to substitute. That is 9. What do we want to substitute in this? We want to substitute the solution that we assumed ui0 plus summation p1 to infinity epsilon p uip xk. This is what we want to substitute in that equation. So, if you take that and substitute here, what do you get? Right. So, you will getCijkl dou by dou xl acting on uk. So, dou by dou xl acting on ui0 plus dou by dou xl acting on epsilon p uk, right. So, that is what we have here when we substituteCijkl dou uk0 by dou xl nj plusCijkl summation p1 to infinity epsilon p dou uk by dou xl nj equal to 0. This is basically substituting this series in terms of the disturbance parameter into my traction boundary condition. Now, you can differentiate this with respect to epsilon and substitute epsilon equal to 0. Okay, let us do that. If you do, what do you get? You get dou nj by dou epsilon here, which has to be evaluated at epsilon equal to 0, and now you differentiate this with respect to epsilon. Epsilon power 1 will give you a term, all the others will give you epsilon squared, epsilon cube, etc. will give you an epsilon term, and because I am substituting epsilon equal to 0, all those terms will go to 0. So, only the first order term survives here. Do you see that? Right?
Why not NG by DXL?
First term.
First term is okay. Second term, if NJ, like in first term we have differentiated NJ by DXL.
Right.
Second term also then NJ by DXL.
Mm.
Equation 23, the second part, which is double NJ by double epsilonCijkl double uk by double xl.
Okay, let us do, no. So, I have to differentiate with respect to epsilon.
Yeah.
Okay. So, let us differentiate. How do you differentiate with respect to epsilon? You will get what terms? Summation, okay,Cijkl common to everything, summation p is equal to 1 to infinity. What are the terms I get? First epsilon will give me what? P epsilon p minus 1 dou uk of p by dou xl nj, okay, plus maybe you keep the epsilon p the same, you differentiate, I am putting epsilon 0, right. Do you see? Okay. So, you do this, these are the only terms that survive, 2 of them, right. That is true even the first one also. C you assume as a constant, but dou uk is 0 by dou xl, right. That is the 0th one, which is not dependent on epsilon. Okay. Now, we already have evaluated dou nj by dou epsilon at epsilon equal to 0, which was minus d delta x by dx delta I1. So, I can substitute here and I can keep this as nj0, where nj0 is delta j2, which is the original unperturbed boundary. Why? We are using 21 here, right. This is what we are using. Do you see this? Okay. So, this is the free surface boundary condition. Now, you have put it, we can, this is another step. So, this is also there in Greenfeld. You can take a look at it. If you have a equilibrium stress tensor Pij0, which is associated with a homogeneous deformation, and if you have an applied stress along some given direction, then this Pij0 is written as tau del ai del aj. Okay. So, we are going to use this, because remember thisCijkl dou u0 by dou xl is basically like Pij, right. It is a constant, the 0th term, which does not depend on the perturbed surface, because it is not a function of the disturbed parameter. So, the first term is basically like some constant sigma 0 about which there is a perturbation because the surface is perturbed, that is what we are looking at in the second term. So, you can substitute this kind of expression into theCijkl dou uk 0 dou xl by taking tau del I1 del j1 etc. So, the effect of all of that is to make all this as 1 1, okay. And then you have this term is as is from the previous case, and then we take a inner product of this. So, there is another dot n, this one I am dotting with n again, okay. Why are we doing? You will see. So, it leads to some expression that I need. So, you take inner product of 24 with u1 1. What does this one mean? This one means in the summation this is the first term, okay. That is what it means, first order term. You have this expression, and where we have also used this fact that if you have a homogeneous deformation, then there is a simpler way of writing this stress tensor in terms of the deltas, Kronecker deltas. So, that is what we have done here. Okay. So, now let us consider the 0th term. What is epsilon wavy? It is half integral 0 to L dx integral over gamma and this gamma dzCijkl dou ui by dou xj dou uk by dou xl. What is this? Elastic energy, halfCijkl epsilon aj epsilon kl. I am integrating, right. Now, when you put epsilon equal to 0, you will recover dou ui by dou xj dou uk by dou xl, which is nothing but the energy of the flat interface. So, we have shown that epsilon wavy with epsilon equal to 0 becomes E flat. Okay, first term is done. Now, the second term, so we are only looking at elastic energy, bulk elastic energy, no interfacial energy. For this there might be an associated interfacial energy, for example, when you have a perturbation. We are not looking at it, we will discuss that in the end. Now, to prove the second result, the necessary condition, you need what is known as Leibniz rule. I do not know, again, I mean it has been taught to you probably, I do not know how many of you remember, but it says that d by dt of some integral at to bt, if you have xt dx, x is the dummy index, so it will get integrated. So, you will have a function of t in which you have to substitute b of t and a of t, that is getting differentiated with respect to t. Then you can take f, substitute b of t, multiply by b prime, which is dou b by dou t, minus f, substitute a, a prime t plus integral a t to b t, you can take d by dt into the f. Basically what we are saying is that you just cannot take this dou by dou t into the integration thinking that integration is with respect to dx, I can take the d by dt, because the end points are functions of t, you have to account for that. So, those are basically the correction terms. If it is not, like if you are doing your Fourier transform, oh, it is only a function of k, I can take a dou by dou x inside, or it is only a function of x, I can take a dou by dou k inside, you can do. But here we are not able to do because the limits are functions of the t. So, that is known as Leibniz rule. Okay. Why are we doing this? Because we want to d by d epsilon, you remember. I have the epsilon w, I need it with respect to d by d epsilon, and I just wrote that energy, right. Now, the d by d epsilon, if I want to do this 0 to L dx is okay, but this gamma is also okay, that is not a function of epsilon, but this gamma is a function of epsilon, right. So, I have to differentiate d gamma by d epsilon and add that correction term with here I substitute and take that as the first term. The second term is of course integral, where I can take d by d epsilon into the integrand, right. So, that is the Leibniz rule. So, if you do, you see that d by d epsilon of energy for the wavy interface consists of two terms. This term is the one where I have taken the integration and multiplied by the d by d epsilon of the, because this is h plus epsilon delta, right. That is how we said the disturbance is undisturbed gamma to which I add epsilon of delta. So, the d by d epsilon of this, which is what gives rise to this delta term. Okay. And this other one is basically where I have taken the dou by dou epsilon inside. But why have I put it only on one of them? Subhash question is still valid, right. I mean, I should have a dou by dou epsilon here, I have a dou by dou epsilon here, right. Look at this, this is half integral this. So, d by d epsilon when I take, of course, there is a correction term, that is what I have written as the second term. First term is d by epsilon, d epsilon is taken in, and there is this term, there is this term, both are functions of epsilon. So, by chain rule, I should do this one and I should do that one. So, there should be two terms, but I have only one term. Why is that? Can you see? Not higher order terms. I am saying, see, I wanted d energy w by d epsilon, right. By Leibniz rule, that will take one dou by dou epsilon inside the integrand and there will be correction term. Now, when I take dou by dou epsilon inside here, this is also a function of epsilon, this is also a function of epsilon, right. So, there should be dou by dou epsilon on this times this plus this times dou by dou epsilon of this, but I have written only one term there. Can you see why?Cijkl symmetric. So, if you haveCijkl dou by dou epsilon acting on dou I by dou xj, that will be the same as dou by dou epsilon acting on dou uk by dou xl. So, I have actually taken that, they are the same, so I made it 2 times this, that is how the 2 got cancelled. See, there is a half here, but in that term there is no half. So, I have actually done it twice, but by symmetry it is the same. So, I made it 2 times this term and 2 and 2 got cancelled. So, I have that expression. Now, we know that integral 0 to L dx of delta is 0, right. Whatever be this term, because it is integrating over delta, this should go to, right. The limits have changed because I am doing at epsilon equal to 0. So, d energy w by d epsilon at epsilon equal to 0, that is why this limit has become just h, all the epsilons have gone. So, this is a constant, in fact that is the same energy as the flat energy, and you integrate it over delta because delta dx is a, by volume conservation, that is 0. So, you have that 0, right. Now, you only have this term which we need to prove that is equal to 0, right. Our aim is to show that the first term is also should integrate to 0. right. How do we do that? Okay, so this is 0, that is fine. I pulled it out because it is a constant, and I have this. How do I prove that this is equal to 0, right? So, how are we going to deal with this? So, you take the dou by dou XL and transfer it to the other variable. We know that pKl0 is a constant, right. So, that is what this is divergence theorem. Instead of doing the integration over volume, you can do it over the surface, and on surface we know what it is, capital gamma and small gamma, and we have already proved that this surface consists of capital gamma and small gamma, and we know that it vanishes on the small gamma by the expression that we derived. You remember we had that pk0 uk1 here. So, we have proved that on the gamma, that is why I dotted taken an inner product with ei1, and that I have shown to be 0. So, on that surface it is 0, on the other surface it is also 0 by the equation 25, that is on gamma here. Okay. So, because of this you now know that this term is 0. So, we have proved that d epsilon w by d epsilon evaluated at epsilon equal to 0 is 0. So, that is the necessary condition that we have proved. Okay. So, this is the only trick. So, you take this integral and you turn it from a volume integral into a surface integral. Surface we already know prescribed traction and prescribed displacement, and we have already derived those results that these quantities are 0 there. Okay. Now, to get the second derivative, of course, you have to take the d by d epsilon of energy W and differentiate it once more. It had 2 terms, now it will get 4 terms because this Leibniz rule is still valid. Okay. One of them is 0, that is why you are not getting, otherwise you will get 3 terms there and 3 times 3 9 terms here. Okay. But one limit is 0, it is a number, it is not dependent on epsilon. So, you get 4 terms, and while doing you have to also use this d by d epsilon is delta of dou by dou z, because delta is dou z by dou epsilon. Okay. So, you can use this, and that is how you get these, and here again you can see when I substitute epsilon equal to 0, this delta term will become 0 by mass conservation, because that is again some constant integrated. So, there are some factors of 2 etc. are missing here, I do not know if you can see. Okay. I think I have explanation of those in the next one. Yeah. So, this is the one, factor of 2 in the third term, it is due to symmetry. The same, you take d by d epsilon, 2 of them will come and so on. So, that is what I am clubbing, and that is how that is coming, but after that this will anyway go to 0. And similarly, by doing this divergence theorem etc. Okay. So, we want to evaluate this at epsilon 0, this consists of 4 terms, and you can show that one term is 0 by this mass conservation. Okay. So, this the second term, again you can take the dou by dou xj and transfer and use divergence theorem and show that this is 0. Okay. Now, third term is has this dou uk 1 by dou xl, but you look at the last term, that is dou ij 0 by dou xj and dou uk 0 by dou xl. So, this is like the homogeneous one, and dou by dou z of that is the constant, and you are taking differential. So, that will go to 0 too. Okay. Now, you are left with these 2 terms, and next we evaluate this third term, that is what I am showing here, dou uj is dou I 0 by dou xj, dou uk 1 by dou xl times delta, and you know that this is Pij. So, you have dou uk by dou x by xl into delta, and Pij 0 you can write in terms of tau del ij, del I1, del j1 etc. So, you have this, and so this I1, j1 etc. make life easy. So, you get tau u11 by dou x1 times delta. Now, this can also be written as this. Okay. this is just purely algebraic manipulation. So, you can write the equation 27 that we derived, this one, right. I dotted with u1 and I got this expression. So, this expression can now be, this again is purely algebraic manipulation, can be written as this. Now, the total term you can write. So, you have this term and you have this term. Here again you can see that there is a delta here. So, if you integrate this, this term will vanish. So, you will be left with these two, and for this now you can use your divergence, Gauss theorem, whatever, so that you can write this also in terms of dou uk, dou xl. Okay. So, once you have written everything in terms of dou ui, dou xj, dou uk, dou xl, you can see that this is half and this is minus of the same quantity. So, it will become minus half. You look at the integrand, it is positive, it has a negative sign. So, it is negative. So, we have proved the second. So, what is it that we have done? We have proved the necessary and sufficient condition for the energy of the perturbed surface to be a minimum. So, if you have small enough perturbation, the wavy interface will always have lower energy, and so it will always break up. Now, we have looked at one end, so it should be small enough that it will break up, but as the surface breaks up, you see that the interfacial area increases, which means there is a wavelength below which the interfacial energy increase will be more than what it can gain by relaxing the elastic energy. So, any wavelength below that will not be promoted. So, that is what it is. Smaller the perturbation wavelength, higher would be the contribution from interfacial energy. So, interfacial energy sets the lower wavelength limit. If there is no interfacial energy, the system will break into the smallest possible interfacial wavelength it can have. Okay. What is setting the lower wavelength limit is the interfacial energy. In the absence of interfacial energy, any wavelength is unstable. We have proved that using the variational methodology. Okay, this is fine. Any questions? Please go through. Unless you do these derivations once by yourself by hand, it is very easy to think that, oh, it is clear, and then you get stuck, like I got stuck here sometime, right? It always happens. Okay.
What will be the wavelength for final structure?
So, this is only a linear stability analysis, right? I have looked at only perturbations which are very close to the flat surface. So, if the perturbation is not there, I recover flat. But as the system undergoes ATG, it is going to move more and more away from this. So, the evolution of the surface after this initial stage, this theory cannot explain. It's exactly like in spinodal. Oh, you can do a linear stability analysis, it will pick the wavelength, but after that how the system evolves is not described by this. That is where you have to do the simulation. Nonlinear terms, long term coarsening that can result from after it breaks up, those will not be recovered from this analysis. This analysis only shows that any wavelength will break, energy will set the lower, interfacial energy will set the lower wavelength limit, there are always perturbations. So, the moment the system gets that perturbation, it will just undergo this undulation. How it evolves further, then you need the nonlinear theories or model it using phase field. Okay. That is one of the reasons why we need to do numerics. I have also assumed isotropic elasticity, right, plane strain, etc. I do not know if I showed you the conditions which we assume. Yeah, so if you look at some of these things that we are assuming, so there are assumptions about the elasticity also and the interfacial energy also. I mean, we are not even considering interfacial energy, that can be anisotropic in solids and so on. So, in all those cases it will fail. So, we cannot use these analysis. This is only to show you that why ATG happens. Okay. Perturbative analysis is relatively simple, but the algebra is horrendous. Okay. In the other case, at least I am able to show, in this case you have to do some maple only to get the solutions. But the cleverness is in the way they write the solution. I will show you I mean, for somebody to have thought about it and written it first, that is the key thing. But other than that, it is rather straightforward. So, let us look at how we do. In this case, I am using Sridhar, Rickman and Strolowitz. There is a nice paper, multi-layer film stability, in Journal of Applied Physics 1997. They also have a follow-up paper in ACTA, I think, around the same time. But anyway, so for what we discuss, this paper is sufficient. So, what we are going to consider is that I have a film and it is embedded inside a matrix, and like I showed with the notebook, there are two ways in which things can buckle. One is called symmetric, the other one, it should be anti-symmetric. This is not asymmetric, this is anti-symmetric. So, what we are going to do is that we are going to write down the elastic solution for such perturbed interfaces to first order and do a linear stability analysis and see whether a given wavelength perturbation will grow or will die, taking into account both the interfacial energy and the elastic energy. Okay. In this case, interfacial energy is also built into the analysis. Okay. So, how do we do that? So, we consider a single misfitting plate, okay. Misfit is included. In the other case, there was nothing like misfit, right. But when you have films, substrates impose a lattice parameter on the film. So, there is a eigenstrain or misfitting strain that has to be included. So, that is what we are doing, but we are assuming that misfitting strain to be dilatational. Yeah, it is more compliant, less stiff. So, Grinfeld did only for vapor, okay, and Asaro and Tiller did for solid with melt, and Strolowitz himself did for solid with another solid, but more compliant. And then people realized that as long as you have any surface which is surrounded by a more compliant surface, this will always be true. Okay. From vapor, from melt, from another solid, people finally concluded that it is. Okay. So, we are assuming that the misfitting plate and matrix are isotropic. We assume that matrix and the plate have the same Poisson ratio and the Poisson ratio value is 1/3. These assumptions, I mean, this for example is not very strict. Okay. You can assume any other Poisson ratio value, but if you assume that they have different Poisson ratio, the writing the solution is very painful, not so trivial. Okay. And we assume that this is a plane strain problem. Under these conditions is how we are going to write the elastic solution to first order for the perturbed interface, right. So, that is where the key is. Okay. So, we assume that the initial matrix is flat, that you can see at plus or minus h by 2. If you have the center h by 2 and minus h by 2, you will have a flat interface. It is independent of x, it is same h by 2 everywhere, right. That is what this initial interface that you have with respect to center, it is always at h by 2 irrespective of what x value you take. So, that is the unperturbed interface. Perturbed interface will be a sinusoidal one with x. The h will be modified by delta cos kx. Okay. Now, you can assume that for plus or minus h by 2 delta cos kx for both the upper and lower, then that becomes a symmetric, and if you assume that one is plus other one is minus, you get the anti-symmetric. So, I am going to do the analysis for symmetric. Anti-symmetric is just a change of sign and some algebraic change. So, that is not a big deal. So, what we want to know is that what is the rate of growth of delta, this is this perturbation amplitude for various wavelengths lambda, right. I can set up one wavelength, I can set up several wavelengths. So, what happens to these? That is what we want to find out. We want to consider both volume diffusion and interface diffusion. Okay. I will do the first interface diffusion, then I will show you how to modify the solution for the volume diffusion. They are rather trivial, except that it involves some arguments, physical arguments. If you know them, then it is trivial. Okay. So, let us call the diffusion potential per atom as pi. Now, obviously gradient of pi determines how perturbations will evolve, because that is what determines the mass flux. Okay. So, all you need to know is what is the diffusion potential when I have a perturbed interface. Now, the interfacial energy will obviously depend on the curvature of this. So, there this is the curvature and this is the interfacial energy. Now, actually I am doing it in 2D, that is why I am just taking one curvature, but if you are in 3D there is a factor of 2. Okay. So, that is what is there in this footnote. And what is the elastic terms that contribute to this diffusion potential? This was derived by Johnson and Alexander. It is a nice paper. Okay. You can also take a look at Sridhar-Rikman-Strolowitz itself. So, what is this term? Can you see? W is strain energy density, and my notation is, if I put a square bracket, that is a jump in strain energy density, there is a matrix precipitate. So, there is a jump. Okay. And this is essential because you will not see ATG instability if both the phases have the same moduli. You can't assume homogeneous moduli and do anything, nothing will happen, because when it undulates it has to relax the elastic energy, which means the other phase has to be less stiff, more compliant. Okay. So, this is basically the jump condition at the interface for the energy. The other one is the jump condition for the displacement or traction, you can think of it whichever way. So, it is T dot del u dot n Pm. T itself is sigma ij dot n. Okay. Okay. Now, how do you get this diffusion potential? Please look at Sridhar-Rikman-Strolowitz, and in terms of stresses and strains, this Wp is nothing but sigma m epsilon m minus sigma p epsilon p minus the eigenstrain, right, because that is a stress free strain that has to be subtracted. The sigma epsilon gives the energy only in the case of elastic stresses and elastic strains. So, from the total you have to subtract the eigenstrain to get the elastic one. Okay. So, this is anyway the jump condition, the difference between the two, and you can see that this T dot del u dot n can also be written as sigma m double dotted with epsilon p minus epsilon m. Okay. The way to think about it is T itself is sigma dot n and this is del u dot n, del u is strain. So, the two dots basically makes it a double inner product or double shrink. Those subscripts are summed basically, which is not surprising because everything is energy, right. Dimensionally you look at the expression, it is a potential, it is a diffusion potential. So, everything is energy. Okay. So, obviously they all have to become a scalar. So, they are becoming a scalar. Okay. Now, the strategy is to evaluate the different terms in this diffusion potential by assuming a perturbed interface and to first order. Why? Because we are going to assume that the delta k is far less than 1. K is basically 2 pi by lambda. So, delta is basically amplitude of the disturbance I am putting, and I am considering the wavelength, and compared to that wavelength this perturbation is very small, that is all the assumption I am making. So, delta is small is basically what I am looking at. So, what do we need to do? So, for the perturbed interface, what was my perturbation description? It is delta h by 2 plus delta cos kx, right. Now, I have to evaluate basically this curvature for this perturbation. How do I get the curvature? Well, there is an analytical geometry result which comes from Courant and John. You can take a look at a classic textbook on calculus and analysis, which shows that if you have a profile, then the curvature is second derivative divided by 1 plus first derivative squared whole to the power 3 by 2. Okay. Now, I have delta cos kx, second derivative will give you minus delta k squared cos kx, first derivative is minus delta k sin kx, right, squared. So, that will become 1 plus del squared k squared sin squared kx, but I am going to take only delta to the power 1, higher order deltas I am going to neglect. So, this I am going to neglect. So, which is approximately minus del squared cos kx. This clear? So, curvature term has been evaluated. So, we know what it is in terms of delta and k. What we need to do is to get an elastic solution for this kind of interface, which is the tricky part, and to get that, okay, for the given interface profile you can't get analytical expression for the elastic stress and strain fields, okay. But you can get displacement fields and evaluate it to first order in del k. Using that you can get approximate strain and approximate stress to first order for the perturbed interface. To do that, we have to solve the equation of mechanical equilibrium. You saw the equation of mechanical equilibrium as del dot sigma equal to 0, right. This is another form. This is where all those assumptions are coming handy, that I am assuming isotropic, that I am assuming plane strain and so on. In that case, in terms of the Poisson ratio, you can write this as the solution for the displacement field. Okay. So, del dot sigma equal to 0 can be reduced to this form. So, I have assumed Hooke's law, I have assumed the elastic moduli to be isotropic and so on. So, all those assumptions are in place. This is the displacement field, and I need to know what this displacement field looks like when I have a perturbed interface. So, that is basically what we are looking at. To do that, so we assume that it is some u0 plus some delta k times u1, and we assume that these are coherent interfaces, and so the displacement and traction fields at the flat interface should obey the continuity conditions, displacement and traction continuity when you have this flat interface. You can see Mura, for example, and they should also obey these expressions, okay. u0, that is in the plate and in the matrix, how it should be when you have the flat interface, you know. So, you can from the solution of this this equation you can show that u0 should be like that, that is for a flat interface. But when you have the perturbed interface, you can see that inside the plate by symmetry at z equal to 0, the displacement component and shear component should vanish, right. You have something that is symmetric about the z equal to 0, plus h by 2 and minus h by 2, okay. And well into the matrix phase if you go, these disturbances that are coming because of the undulation should be 0. That already gives you a hint that you should use some sine hyperbolic, tan hyperbolic kind of solutions, so that they will die well into the bulk, and that is what is written. So, u1 is some cos hyperbolic plus sine hyperbolic and sine hyperbolic and cos hyperbolic and cos and so on. This is within the plate, this is within the matrix, okay. Now, why is this the solution? Well, this is the ansatz. We say that this is the solution. We find the P1, P2, M1, M2, which will then, how do we get P1, P2, M1, M2? By using those conditions, right. It has to obey the equation of mechanical equilibrium, it should obey this u1 going to 0 as you go z infinity and so on. So, we put, so which means you are going to get lots of algebraic equations in terms of P1, P2, in fact 4 of them, right, 4 unknowns. So, you need 4 equations that has to be solved, and these are all cos h, sin h, cos, sin, etc. So, this is what makes the algebra very messy, and that is where you have to use Maple or Mathematica to solve, okay. The constants are evaluated by applying the displacement and traction continuity conditions, and expand up to first order, throw away the higher order terms, okay. When we do, you get a matrix equation A x equal to b, where A is this matrix and x is the unknowns P1, P2, M1, M2, b is basically this 0 to epsilon t by k, 0 to epsilon t by k. Now, what are these c, s, omega, etc.? It is here. C is cos h and s is sin h, and rho is the ratio of the Young's modulus, and we have assumed the Poisson's ratio to be equal and equal to 1 by 3, and omega is nothing but kh by 2. So, there is a Maple script that I have posted where all this is done. You take this, you put it, you expand, keep to the first order terms and generate the matrix and solve it, and the solution will happen to be this. All this is there. So, you can take a look at, but here also when you have this h by 2 plus del cos k x, the interface normals have to be evaluated when you need n1 and n2. The same thing, how did we evaluate interface normals there? You remember minus d inverse d by dx of this. So, they are true here also, and again taking to first order in delta, you can show that n1 is del k sin kx, n2 is 1. Okay. n2 is 1, you can see, because it is just d inverse. So, d inverse has this del squared k squared, and we said that because del squared is higher order we will leave. So, 1 is what will come. So, square root of 1 will become 1. It is 1 by 1 plus del squared k squared sin kx, and so sin squared kx, and so it will get. So, it is the same. So, you will see it in many different forms. So, this is from Freund and Suresh I am showing you, but there we use Riley, Hobson, Binns and Thomas and Finney, but it is the same. Okay. So, you can evaluate, and there is this horrendous expressions for P1, P2, but before we go there, okay. So, if you have the elastic solution, if you have the curvature, you can substitute into the diffusion equation and get the growth rate, right. That is basically what we want to do, and that is what is being done. So, let us say that we have interface diffusion, and at the interface the atomic flux will be given by the gradient of the diffusion potential, right. I am considering this curved interface, I am considering the interface diffusion. So, if interface is parameterized by S, dou phi by dou S will basically multiplied by mobility will give me my flux. This is a fixed law, right. And so, for small perturbation, Freund and Suresh also show that you are almost in x y only, the S is not changing much. So, you might as well take the derivatives with respect to x and y. For this is true only if the delta is very small compared to the lambda that you are. Okay. So, if you do, then you can see, so if the material is brought by interface diffusion, the material, the interface will move. So, the velocity of the interface is nothing but the molar volume times dou j by dou s. You can see j is what, number of atoms per unit area per second, and you take a gradient. So, it is per unit volume per second multiplied by the molar volume. So, it is number of atoms per second. So, that is basically a velocity. Okay. So, and you can substitute here for j. So, you have velocity as mva times del squared phi by del s squared. Okay. But you can also get the velocity by taking the normal and dotting it with how the x is changing, and we have already assumed the interface profile. So, we can get the velocity. So, dou delta by dou t is cos kx approximately, where we have thrown away any term which is del squared and so on. So, you can see that dou delta by dou t times cos kx is this expression, and we know all these terms. If you know P1, P2, M1, M2 of course. So, you can substitute here and you can look at the growth rate, right. So, if you do, let us say that all this is some, you can see at least for example del squared phi by del s squared, just look at the curvature term, right, that we evaluated, right. It will have gamma and it will have del k squared cos k x, right, and you will take derivative with respect to x. So, it will give you k squared and so on, right. So, you can see that it will have some del and some k squared expression, right, that you can see at least from one of the terms. It will be similar in other terms also. Let us collect all those terms and call that as some g. Okay, I will show you what the g is. Times delta times cos kx. So, cos kx will go. So, d delta by delta is nothing but g dt, which is our usual trick. You can integrate it easily. So, del t is del 0 exponential gt. Now, the sign of g will tell whether this is going to grow with time or not. So, what is g? So, the g is written in non-dimensional terms, Okay. This h power 4 is coming because you have k power 4, and you saw at least in the curvature term where the k power 4 is coming, because it is del k squared cos k x, and del squared by del s squared will give you 2 k squared. So, it will be k to the power 4. Okay. So, you can see that this is coming from the curvature and this is coming from the elasticity, and theta is this elastic energy normalized by the interfacial energy. You can see it is like some sort of length scale, because I mean interface is going to set the wavelength. So, as compared to elastic energy, how much is part of it, and this f is this very complicated function, where you have these a, b, d constants which are also complicated functions. All this you can get only from Maple. Okay. So, let us go back and look at what is it that we are doing. I mean, you just want the growth rate and you want it to be in terms of the delta. Okay. And because you have put a sinusoidal one, you substitute the causes and sines will remain and they will get cancelled on both sides. And it is exactly like we put in the diffusion equation cos kx and found the growth rate, and found that in the case of diffusion they are always dying, all wavelengths, right, it was homogenizing and so on. So, we are doing basically the same thing, that is the perturbative analysis. Only thing that we have not done so far is that we have looked at only the surface diffusion, and surface diffusion had this del squared by del s squared which gave a k squared, and added to the del k squared which you had from perturbation for the curvature gave you k power 4. Now, what happens if the diffusion is not surface diffusion but volume diffusion? Okay. Now, in the case of volume diffusion, instead of the k power 4 that you saw in the expression here, you are going to get kh to the power 3. Okay. Now, why? This is physics and this is some really old physics, but really beautiful physics. You should go back to these papers and see. One is from Herring, effect of change of scale on sintering phenomena in Journal of Applied Physics in 1950, and he makes a couple of assumptions that diffusion is divergence free. What does that mean? Dou c by dou t is del squared c, divergence free is del squared c equal to 0. So, basically that is the assumption, and you know diffusion in solids has to happen by vacancy mechanism, let us say. Then there should be enough vacancies available for the system to freely do this or evolve, or kinetics should cope up with it. In other words, you might have a driving force, and if you do not have enough of kinetics, you might still not get it. So, they assume that kinetically the system can relax. Making those two assumptions, you can show that J is nothing but k phi. Remember, surface diffusion gave J as what? Del phi, but in this case J is just k phi. These are really nice arguments and very beautiful arguments, both in Mullin's, and Mullin's paper is also a classic. Those of you who have done dendritic analysis, Mullin-Sekerka. So, this is basically a precursor to Mullins and Sekerka. So, he takes a flat solid and puts an undulation and sees what happens, doing a linear stability analysis. So, that is this paper, and Herring's is also very nice. Any case, so J is k phi and V is Va times J we know. So, we know that it is k times phi, and you saw that phi gave you a k power 4, but here is a k that is multiplying. So, it will give you a k cube. That is how it is kh cube dependence. Okay. Now, Sridhar Srolovitz does not have, or in some place they just mention that if it is volume diffusion it will be this, and you have to go back to this Mullin's paper to see. Mullin's actually considers surface diffusion, volume diffusion, evaporation condensation, all these mechanisms, how the kinetics will change. They basically change the exponent of these terms. So, that is basically what they show. So, there is also this other nice paper which is slightly hard to come by, but we do have a copy of this. Nichols and Mullin's surface and volume diffusion contributions to morphological changes driven by capillarity. So, in all these cases, see, elasticity solution is the same, we do not have to worry. the curvature term is what will change depending on the diffusion mechanism, and that can be obtained as kh cube, kh power 4. I do not remember what it is for evaporation condensation or dissolution deposition, maybe kh squared or something like that. So, it is there, you can take a look at and you will see the kinetics. Okay. So, that brings me to almost the end of this lecture. We have done one case where it was static, the other case perturbation, that is also for static, we did not allow for any new flux, but you can extend this analysis for dynamic systems. That has been done by Spencer, Voorhees and Davis. It is in PRL 91, it is a nice analysis, so you can take a look at it. Okay. But of course, you do not have to do such complicated analysis if you have access to modeling, which is the reason why we are doing modeling, and you can relax all these assumptions. You can relax the assumption of isotropic elasticity, you can make the interfacial energy anisotropic. There is a nice paper by Torabi and Lowengrub, I think, where they use a nice way of incorporating interfacial energy anisotropy using higher order tensor terms and look at the evolution of thin films in some silicon system, silicon germanium. Okay. So, like we discussed slightly earlier, nonlinear long time solutions etc., you cannot do with this kind of analysis. So, you need simulations to understand them. Coarsening, for example, generally there is a breakup, after breakup the system will coarsen if you have a thin film. So, those kind of things are not there in this kind of analysis. You can do coarsening analysis like LSW, but that is a different analysis that will not follow from what we have done so far. And what is the effect of dynamic instabilities, for example? Okay. So, I can have some source of material to my film as it is undergoing ATG, then what happens, right? So, you can go do the analysis, but you can also do it using simulation. So, this is, I mean, the entire lecture that I gave is part of a book chapter, and for that Sushil generated lots of simulation results. I will show a few of them to conclude. Okay. Now, this is static instability in the sense that the black region is matrix and the 4 figures tell you with time how the system is evolving. So, we had a thin film with a flat interface which developed undulations and then they broke up and they entered into a coarsening regime. So, you can see, for example, in this part these are smaller compared to the ones next to them because they are losing material to the next one because of Gibbs-Thompson. Okay. So, this is static because he had very little of supersaturation in the matrix. The moment you add some supersaturation, of course, the films are also becoming thicker, and when they become thicker, the time for breakup also will increase. So, you can see the length scales in this system are very different and the coarsening is still there. So, this is, you can also look at the effect of adding a flux to the film that is undergoing ATG instability. Okay. And of course, you can put now more than one film. Sridhar Rickman-Strolowitz also has a paper with several films in the simulation domain, not just one single film. And we ourselves have done some simulations long back, where we keep the volume fraction the same, but the number of films to be different. What is the effect of that, and so on. So, here you can see an interesting thing, which is what is exploited in quantum dot formation. Wherever, so you see this kind of triangular regions that are forming, right. So, if you have 2 peaks in this film and in between that the other film peaks, that is because of elastic interaction between films. So, the films can sense the other one. So, if it peaks here, then that film will have a trough there. So, it will have a peak in between where these two have a trough and so on. So, they adjust themselves, and that is what leads to, and this is very clearly seen in this kind of triangular structure that you see here. Okay, that this is coming because of the interaction between the films, elastic interaction between the films. So, you can study these kind of things in the simulation. And of course, that is a static case, and here is a dynamic case where, I mean, this is beautiful, right. Okay. So, here there is some supersaturation in the matrix. So, as they are undergoing transformation, they are also breaking, and you can see long term looks very different here compared to the previous one. Okay. So, all this you can put in the simulation and study, and of course, you can also do 3D, where we have an isotropic system, a film which is undergoing instabilities, and we have an anisotropic system, elastically anisotropic, elastically isotropic and elastically anisotropic. We have not assumed anything about the interfacial energy, which can also be highly anisotropic in systems like silicon, germanium and so on. But this one is with the elastically anisotropic. I do not know if you can see, but there is this 45-degree angle that is preferred by these precipitates. Okay, so that brings me to the end of this lecture.